All right. Good morning, class. It is Monday, April 13th, and I hope you guys all had a good spring break. It was for us here at the house. We did a lot of building. I started this project here helping out some of the local hospitals. We are 3D printing these face shields and putting masks on in front of them. So we've got a whole batch of those and helping the folks around here. Also got a chance to build out the chicken coop. I can show that to you guys later the week. But anyway, for those of you guys who missed last week's message on Friday, we have a few housekeeping things to talk about here. The biggest thing is just to talk about the new proposed remote learning schedule and the plan going forward here. For at least the foreseeable future. Right now, as it stands, we are at a stay-at-home order until the end of the month. That is April 30th. And so we are going to try to continue moving on day by day with our classes. Hopefully you're getting a similar message from your other teachers, but for physics, the plan will be as follows. I'm going to post 2 videos a week, so Monday and Wednesday. There will also be 2 assignments each week. From last week, there was worksheets 1 and 2. Those videos and links are all on Google Classroom. If you can't find those, let me know. Also, as a reminder, I posted quizzes number 2, that is due today. So hopefully you didn't finish that. Make sure you get that done and turned in. Here's a link. I will post these slides as well on Classroom. So, and just to show you, this is at least the planned remote learning schedule that we are all using at Vaughn. I'm ignoring the Monday through Thursday schedule. Monday through Thursday, I will be available from 10 to 2 here. But we aren't going to be meeting synchronously. But if you need to get a hold of me, feel free to send me an email, and we can figure out whatever I can do to help you. So Monday, Tuesday, Wednesday, Thursday, my plan is those 2 videos, 2 assignments, and then on Friday, I will send out a meeting invite for each of you to come in, and we'll just do a discussion and a debrief on the week's topics. So from 10 to 10:30, and we won't go the full 30 minutes, but let's say 25 minutes from 10 to 10:25. First period from 10:30 to 10:55. Second period from 11 to 11:25. Third period, etc., right? So that's the plan, and we'll see. We have to be flexible, so we'll play this by ear. So if you have questions, let me know. All right, so I want to jump into today's topic. Last week, or the week before, we talked about simple harmonic motion, things that are swinging back and forth, things that are oscillating, going back and forth. And this introduces a concept we call waves. So waves are another interesting thing that seems to go back and forth or happen repeatedly over and over again. And so we're going to introduce a few concepts here. The first is the definition of what is a wave. So a wave, we've probably seen these out at the lake or in the water or a variety of other places, but a wave is basically a disturbance that's transmitted from one place to another. And what's interesting, and I want to emphasize this, with no actual transport of matter. The stuff doesn't actually move, but energy moves. So hold on to that thought. I'm sure you guys have some questions, but let's just take a look at what this might look like. So if you were to drop a pebble or stone or water into a pool, you end up getting these ripples, right? The ripples move outward from the center. Now, the water droplet creates a disturbance. It causes the water to go up and down, and that disturbance moves outward. Where's my mouse? That causes this wave to move outward, but the water is actually not moving out. And I want to be clear about that. The water itself is not moving out. It's just the water was dropped down, so it was causing this up and down motion. But we can see that something's happening. Energy is being transported outward, and we call this concept wave propagation. So if you've ever been to a football game or a basketball game, you probably have seen the wave where everyone kind of puts their arms up, and that wave propagates from one side of the stadium to the other. And in this case, the people, the individuals, aren't moving, right? We're not moving. We're just going up and down. But you can see that there's this thing, this wave is propagating. It is moving. And in this example, these soldiers are each going up and down. But we can see that that wave is moving from the right-hand side of the screen to the left-hand side of the screen. So there are two major types of waves. We group them into what we call, the first type is called a transverse wave. And that's similar to this case where the particles are moving up and down. So here the particles could be the soldiers or the soldiers' heads. But a transverse wave, the particles are moving perpendicular to the wave. So the particles are moving up and down, all right? Let me make sure to do this, up and down. But that means that the wave is propagating from left to right. And so if I look at this slinky here, the atoms of the slinky aren't moving, but this disturbance, this jiggle, this movement is causing that disturbance to move down the length of the spring. The second type of wave is what we call a longitudinal wave. Oh, did I define this one? This is what we call a transverse. And the word transverse literally means perpendicular. So a transverse wave means that the particles move perpendicular to the wave. The second type is called a longitudinal wave. And a longitudinal wave, if you look at this one, it's slightly different in that the spring or the wave itself isn't going up and down, but in fact it's going side to side or in the same direction along, that's this word longitudinal, along the same direction as the wave motion. And what you're seeing here is actually a compression, right? We're creating a compression wave, and that compression is now propagating or moving down the length of the slinky. So we're creating that compression, right? So compress, and then it moves all the way down the length of the spring. And there's two major parts of a longitudinal wave. And we'll come back to this when we talk about sound. But the two parts are what we call the compression. That's where we create that compressed part of the spring. And then the uncompression, or the expansion. And the fancy word that we use to define that is called rarefaction. So compression and rarefaction. And you can see that it's propagating, or it's moving from left to right. So we talked about water as the original example. Water waves are actually not truly transverse or longitudinal. In fact, waves in the ocean and in lakes and large bodies of water are a little bit of both. So, and this is really just for fun to look at, but if you were to look at the way the water particles or the water molecules are moving inside a wave, they actually do this circular motion. They go up and down, and they go left to right, but they actually kind of circulate back and forth like this. And as you get closer to the shore, you end up getting these things called undertows, right? So some of you may have heard this, where you get this swirling, the water hits the bank, and then you get this surge of current or water rushing right back. And in really bad weather situations, that can be really dangerous, and it can just suck you or pull you straight under into the water. But this is that motion that we're talking about. This is the motion that the water is moving. And so it does go both up and down, left and right. But this wave here, this water, the actual molecules, the particles here, aren't moving all the way over here. If you were to put a die or a buoy or something here, that stuff is not moving all the way over here. It's just kind of circulating around and around here. And so this is just the nature of how waves work. So, quick review on the anatomy of waves. And this is similar to what we looked at when we looked at simple harmonic motion. Waves have all the same kind of characteristics. They have an amplitude. The amplitude is the displacement, or how far or how high that wave is from the rest position or the equilibrium. So in the water, that would be the zero part of the wave, or the flat part of the water. And the amplitude would be the peak measured from that center point. The peak of a wave is also called a crest, right? So that's the top part. And then the bottom part of the wave we call a trough. So crest and trough. And in this case, for this example, we're creating these waves, and the waves moving from left to right. And we can measure the wavelength of the wave from crest to crest or from trough to trough. That length is what we call the wavelength. And we're going to introduce a new funny character. It's called lambda, which is this symbol right here. Lambda is a Greek symbol that is used to represent the wavelength of a wave. So lambda is the wavelength. So when we wanted to calculate the velocity, or how fast this wave is moving, the velocity depends on a couple things. So the wave has to have a thing to move through. So we call that word a medium. The medium in the case of waves in the water is the water. Waves with things like sound is the actual air particles in the room. This is one of the reasons why sound does not travel in space, right? There's no air or in a vacuum, I guess, right? So the simple equation, the simple model that we have to represent the speed of a wave, or the velocity of a wave, is lambda times f, which is the wavelength times the frequency. Wavelength times frequency. So I told you I was going to talk a little bit about sound waves, and I just want to give you guys a model to picture here of what's going on with a sound wave. So sound is created by the compression and expansion of air, right? So air is being compressed and expanded, and a speaker here creates that. There's this what we call a cone on the front of the speaker, and that moves back and forth. If you have ever looked at speakers, especially playing really low tones, you can hear it, or you can actually feel it moving back and forth. If you were to look at the inside of a speaker, you'd actually see a coil and a permanent magnet. And if you recall from our last unit, we talked about how a moving current in a wire creates a magnetic field. And that magnetic field feels a force when it's in another magnetic field, right? So you've got this wire. The wire has electricity running through it, and that's creating this magnetic field. And that is now inside this permanent magnet, and it's causing that whole cone to move back and forth. And you end up getting these air particles get compressed, and it bombards or pushes the other air particles next to it, that then creates the next one, and you end up getting that movement, or that propagation of energy through the air. And now it's not a constant in all cases, but for all the problems that we're going to look at, for most of the problems we look at here in this unit, we can assume that the speed of sound in dry air at 20 degrees Celsius is 343 meters per second. And you'll notice that I put a couple key characteristics in there. So the speed of sound in dry air, which means that humidity would make a difference, at 20 degrees Celsius, so the temperature also makes a difference, is 343 meters per second. So if it were more humid, if it were hotter or colder, all those things would affect the speed of sound. But for the problems and things that we'll work on here, we can assume that it's 343 meters per second. So the last couple things I want to show here are other places where you might see a wave. And so if you have a jump rope at home, or a string, or probably even your belt, you can do this, where I create a wave by snapping it, right? And here's a little simulation where I can create this snap and it creates the wave, and it hits the end, and you'll notice that it gets reflected back. And not only does it get reflected back, but the wave starts at the top of the string. We'll wait for it here. Starts at the top of the string. When it hits the end, it gets reflected, but not only reflected, but it also gets inverted. And we're going to come back to this idea later this week. But it gets reflected and inverted. In this model, there's a couple things that we could play with, and we'll play with this model later in the week. But damping in this one, you'll notice that the amplitude of that wave is decreasing as it's moving from left to right. And also, I changed the tension in this little animation. So watch this. This is high tension. And now here's low tension. And you'll notice that the tension seems to also have an effect on the speed of that wave. So high tension and low tension. Right? So some of these things are interesting, and we'll take a deeper look at this later in the week. But for this week, or for our first problem set, just a few problems around calculating the speed of waves. And so using the wave equation. So a couple example problems that I'm going to give you guys, and then you guys can work on this. So here's an example problem. A wave has a frequency of 50 hertz and a wavelength of 10 meters. What is the speed of the wave? And so speed, we see speed means the same thing as velocity. So list the variables. F equals 50 hertz, lambda equals 10 meters, and I want to find what the velocity is. So write down the equation, V equals lambda F. We rearrange it. We actually don't have to do anything because it's the same equation. And then we plug in our numbers. V equals 10 meters times 50 hertz, or 500 meters per second, right? So pretty straightforward. And if you look at the units here, you'll notice that lambda is in units of meters, 10 meters. 50 hertz, 1 hertz is the same thing as a 1 over second, or cycles per second. So 50 cycles per second, this is 500 meters per second. So that's how the units work. And our second example is here is a sound example. So the average human hearing range is about 20 hertz to 20,000 hertz. And as you get older, so for me, I think my upper hearing range is probably closer to 14, 15 kilohertz. For you guys, it's probably much higher. But the average hearing range is from 20 hertz to 20,000 hertz. Middle C, if you've played the piano or do anything with musical instruments, middle C has a frequency of 261.6 hertz. And the question is, what is the wavelength of this note? How far is it from peak to peak of that wave? And we can assume that the speed of sound is 343 meters per second in dry air at 20 degrees. So again, we list the variables, 261.1 hertz. The velocity is 343 meters per second, and we want to find lambda. So the first thing is we write down the equation, V equals lambda F. In this case, we want to solve for lambda, so we have to then divide both sides by F. So we rearrange the equation. Lambda is equal to V divided by F, and then we solve. So we plug in our numbers, we punch into our handy-dandy calculator, and you get 1.31 meters. So just to give you guys an idea of roughly how long or how wide the wavelength is for sound, for kind of an average note that you might hear, 261 hertz, it's a middle C, is about 1.31 meters. So it's, what is that? It's about 4 feet-ish, right? So, and then the last slide here for you guys are just some useful relationships and equations that you may want to jot down if you don't already have them in your notes. The velocity we just introduced in these slides is V equals lambda times F, or the wavelength times the frequency. The equation for velocity has not changed from the beginning. V equals delta x over delta t. You may also do that as the distance divided by the time. Period, this is capital T, period is equal to the amount of time divided by the number of cycles, time per cycle. And then the frequency is the number of cycles per time. And the relationship between these two, between period and frequency, is period is equal to 1 over f, or the reciprocal of frequency. And the last little table here, just to help you out, are just some notes. Wave speed is represented by the symbol v, measured in units of meters per second. Frequency is f in hertz, and period is capital T, measured in seconds, and wavelength, lambda, is measured in the units of meters. So I hope that's helpful, and this will be posted along with worksheet number 3. And if you have any questions, send me an email, and I hope you all are doing well. Take care. Bye-bye.